good evening. Tonight, there is nowhere you need to go, nothing you need to solve, nothing asking for your attention. Just let your breathing become slow and steady as we begin one of the gentlest journeys in the universe. Tonight, we are visiting black holes. Perhaps no objects in space have inspired more mystery. People imagine them as cosmic monsters, silent vacuum cleaners, or endless doors into another universe. But the real story is much calmer, much stranger, and in many ways, far more beautiful. So settle comfortably. Allow your shoulders to soften. Feel the weight of your body supported beneath you. As each breath leaves your lungs, imagine your thoughts becoming lighter, drifting away, like tiny stars disappearing into the morning sky, far above Earth, beyond our moon, past the bright planets, beyond the frozen edge of our solar system. The galaxy stretches in every direction, hundreds of billions of stars, slowly orbiting around a quiet center, each star moving so gradually that even over thousands of years, the night sky would seem almost unchanged. Space is not rushed. Nothing hurries. Everything follows gentle paths, guided only by gravity. Gravity, the invisible conversation between every piece of matter in the universe. It is gravity that keeps your feet on Earth. Gravity keeps the moon circling our planet. Gravity guides the planets around the sun. And gravity, when enough matter gathers together, can create something extraordinary. A black hole. Despite their dramatic reputation, black holes are surprisingly simple. They are not holes in space. They are not tunnels or hungry mouths. They are places where matter has become so tightly packed that gravity grows incredibly strong. Imagine holding an apple. Now imagine squeezing it smaller and smaller without removing any of its mass. The weight stays exactly the same. Only its size changes. Imagine continuing, compressing it beyond anything physically possible. Eventually, all that mass would occupy an unimaginably tiny region. Gravity would become stronger, not because more matter appeared, but because the same amount of matter occupied far less space. Nature normally prevents objects from collapsing forever. Atoms push back. Electrons resist. Neutrons resist. But sometimes, inside the largest stars, gravity wins. And when gravity finally becomes stronger than every force trying to hold matter apart, a black hole is born. That sounds dramatic, but the universe does not celebrate. There is no cosmic applause, only silence, the quiet continuation of gravity doing what gravity has always done. The first people who wondered about such objects did not have giant telescopes. In the 18th century, long before astronauts, before rockets, before photography, a few curious thinkers imagined something astonishing. What if a star became so heavy that even light could not escape? It sounded impossible. After all, light seemed unstoppable, yet mathematics quietly suggested perhaps such an object could exist. The idea rested quietly, almost forgotten, for generations. Then, over a century later, Albert Einstein introduced a new understanding of gravity. Instead of imagining gravity as an invisible pulling force, Einstein described space and time together, woven into a single fabric. Everything with mass gently bends this fabric. Imagine placing a smooth blanket across a floor. Now place a heavy bowling ball in the center. The blanket sinks. A marble rolled nearby naturally curves toward the bowling ball, not because anything grabs it, but because the surface itself has changed. Space behaves something like that. Stars bend space. Planets bend space. Galaxies bend space. Even you. Bend space ever so slightly. Around Earth, the curve is gentle. Around the Sun, the curve is deeper. Around a black hole, the curve becomes incredibly steep. Not because space is broken, but because gravity has become extraordinarily concentrated. This is one reason black holes are so fascinating. They are not exceptions to physics. They are physics, following its own rules, to their most extreme limits. As our peaceful journey continues, we'll slowly discover how giant stars end their lives, how black holes quietly shape galaxies, how scientists learn to photograph something that cannot be seen, and why these mysterious objects may actually help us understand the entire universe. But for now, there is nothing to analyze, nothing to memorize. Just listen and imagine yourself floating peacefully among quiet stars, while gravity gently guides every world, every moon, every comet, and every black hole. Through the endless calm of space, take another slow breath and drift deeper into the story. The universe is patient. A single human lifetime is only the briefest moment compared with the lives of stars. Some stars shine for billions of years, burning quietly, with remarkable consistency. Our own sun, for example, is nearly halfway through its long life. It has already been shining for about 4.5 billion years, and it will continue glowing for roughly another 5 billion. There is no hurry. The sun wakes each morning, not because it chooses to, but because deep inside its core, gravity and heat remain perfectly balanced. Gravity constantly tries to squeeze the sun inward. At the same time, the incredible heat produced by nuclear fusion pushes outward. These two forces have lived in harmony for billions of years, like two gentle hands, holding one another in balance. This quiet balance is what allows stars to shine. Deep inside every ordinary star, hydrogen atoms come together. Under tremendous pressure, they combine, forming helium. A tiny amount of mass is transformed into energy. That energy begins an unimaginably long journey. It may take hundreds of thousands of years to slowly work its way from the star's crowded center to its glowing surface. Eventually, one tiny particle of light finally escapes, traveling across space. Some of those ancient particles left the sun just over 8 minutes ago. Now, they softly illuminate the room around you. The warmth you feel on your skin during the day began its journey deep inside the sun, long before it ever reached Earth. Stars are quiet factories of light. They spend nearly all their lives doing exactly this. But every fuel supply has an ending. Slowly, almost imperceptibly, hydrogen becomes less abundant. Fusion begins to slow. Gravity notices immediately. Whenever fusion weakens, gravity presses inward just a little more. The core becomes hotter, denser, more tightly compressed. For stars similar to our sun, this creates a peaceful transformation. The outer layers expand. The star becomes a red giant. Its light grows softer, its surface cooler, even while its size becomes enormous. One day, far in the distant future, the sun may become so large that Mercury disappears inside it. Venus follows. The fate of Earth remains uncertain, but none of this will happen for billions of years. Long after today's mountains, oceans, and cities have changed beyond recognition, eventually, the sun will gently release its outer layers into space. Beautiful clouds of glowing gas will drift outward, forming what astronomers call a planetary nebula. Despite the name, it has nothing to do with planets. Early astronomers simply thought these glowing clouds looked a little like distant worlds. At the center, a tiny white dwarf remains, about the size of Earth, yet containing nearly half the sun's original mass. Dense, quiet, cooling, over trillions of years. That is how stars like our sun grow old, not with violence, but with remarkable grace. Yet, some stars begin life far larger, 20 times the sun's mass, 30 times, sometimes even more. These giants live very differently because they are so massive. Their gravity is much stronger to resist that enormous pressure. Their cores burn fuel much faster. Instead of living peacefully for 10 billion years, some giant stars survive only a few million. In cosmic terms, they are brief, brilliant, and energetic. Inside these giants, fusion continues, creating heavier elements. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen. Oxygen becomes neon. Neon becomes silicon. Silicon eventually creates iron. And this is where everything changes. Iron is unlike the earlier fuels. Fusing iron does not release energy. Instead, it consumes energy. The engine that has supported the entire star begins to fail. Gravity, which has patiently waited for millions of years, finally gains the upper hand. The core collapses, not slowly, not over centuries, but within seconds. Matter falls inward at astonishing speeds. Electrons combine with protons, forming neutrons. The collapsing material suddenly reaches unimaginable density. Then, the outer layers crash inward, strike the compressed core, and rebound outward. A supernova begins. For a brief moment, one dying star can outshine an entire galaxy. It becomes one of the brightest events the universe ever produces. Heavy elements: gold, silver, uranium. Many of the atoms inside our own bodies are scattered across space. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged inside ancient stars. Every person, every tree, every ocean contains material that once lived inside suns that disappeared long before Earth existed. In a very real sense, we are children of ancient starlight. After the supernova fades, something remarkable remains. If the collapsing core contains enough mass, gravity refuses to stop. Even neutron matter cannot hold against it forever. The collapse continues, smaller, denser, more compact, until, according to Einstein's equations, a black hole forms. No explosion creates the black hole itself. The explosion happens around it. The black hole simply appears where the star's core could no longer support its own weight. And then, everything becomes quiet again. The brilliant light fades. The expanding cloud drifts peacefully outward. The newborn black hole sits silently where the giant star once shined. Invisible, patient, not racing through space, searching for victims, simply existing. Its gravity, no different in principle from the gravity of Earth or the Sun, only much, much stronger. Near its center, the universe continues. Calmly, stars are born, stars grow old, stars disappear, new stars form from the material left behind by earlier generations. It is a slow, endless cycle, a quiet recycling of light, gas, dust, and time itself. As you continue drifting through this peaceful story, imagine one of those distant stellar nurseries where clouds of glowing gas slowly gather, ready to become the next generation of shining suns. And somewhere, far away, a newly formed black hole waits silently, its journey only just beginning. Now, our journey carries us farther, beyond the places where individual stars quietly live and fade. We begin to see something much larger, a galaxy. Imagine floating far above our own Milky Way. From this peaceful distance, it resembles a great spiral. Graceful arms, filled with stars, curve gently around a bright center. Clouds of glowing gas drift between them. Dark ribbons of cosmic dust trace delicate patterns across the light. Our solar system is only one tiny point within this enormous structure. If the Milky Way were the size of a continent, our entire solar system would be smaller than a grain of sand. There are, perhaps, 400 billion stars here, each one following its own slow path, each one guided by gravity. For a very long time, astronomers wondered what lay at the galaxy's heart. The center seemed unusually crowded. Stars moved there much faster than expected. It was almost as if something enormous, yet invisible, was holding everything together. Night after night, year after year, powerful telescopes watched. The movements were tiny, barely noticeable, but decades passed, and little by little, a remarkable picture emerged. Individual stars could actually be seen, orbiting something completely dark. One famous star, called S2, takes about 16 years to complete a single orbit. At its closest approach, it races through space at several percent of the speed of light. Nothing ordinary could hold a star moving that quickly, only something with an incredible amount of mass packed into a surprisingly small region. The evidence became overwhelming. Hidden at the center of our Milky Way is a supermassive black hole. Astronomers call it Sagittarius A star. Although the name sounds dramatic, it is surprisingly quiet. It contains roughly 4 million times the mass of our Sun, yet most of the time, it simply rests, patient, almost silent. Many people imagine a black hole constantly swallowing everything nearby. The reality is much gentler. If our Sun could somehow be magically replaced by a black hole with exactly the same mass, Earth would continue orbiting almost exactly as it does today. The seasons would disappear because there would be no sunlight. The oceans would slowly freeze. Life would end, but our orbit would remain nearly unchanged. Gravity depends on mass, not whether that mass is a star or a black hole. This surprises many people. Black holes are not cosmic vacuum cleaners. They do not pull distant objects toward themselves any more strongly than any other object of equal mass. To fall into one, you must first come very close, very, very close. Space itself is mostly empty. The average distance between stars is enormous. Even inside crowded galaxies, black holes spend much of their existence with nothing nearby at all. Quiet, invisible, waiting. Sometimes, however, a wandering cloud of gas or an unlucky star drifts too close. As material begins to spiral inward, it does not fall straight down. Instead, it circles again and again, forming a glowing disk. Each orbit brings the gas slightly closer. Friction heats the material. Temperatures rise to millions of degrees before crossing the edge from which light cannot escape. The gas shines brilliantly. Ironically, black holes themselves produce no light, but the material falling toward them can become among the brightest objects in the universe. Some supermassive black holes power enormous jets. These narrow beams shoot outward from regions near the black hole. At nearly the speed of light, they stretch for thousands, sometimes millions, of light years. Like cosmic lighthouses, they shine across the darkness for billions of years. And yet, the black hole itself remains invisible. Astronomers must study its surroundings, the motion of nearby stars, the glow of hot gas, the bending of distant light. These clues allow scientists to map something they cannot directly see. It is rather like watching leaves dance across a quiet pond. You may never see the fish beneath the surface, but the ripples reveal its presence. Gravity leaves ripples too. Every orbit, every curve, every tiny change tells part of the hidden story. As telescopes improved, scientists realized our galaxy is not unusual. Almost every large galaxy appears to contain its own supermassive black hole. Some are millions of times heavier than the Sun, others billions of times heavier. The largest known are difficult to imagine. Their event horizons can be larger than our entire solar system. Yet despite their size, they still spend most of their existence doing very little. Silent, patient, almost peaceful. In many ways, they are less like monsters and more like ancient mountains, always present, rarely changing, quietly shaping the landscape around them. No one knows exactly how the very first supermassive black holes formed. Perhaps they grew from smaller black holes. Perhaps enormous clouds of gas collapsed directly. Perhaps the young universe offered possibilities that no longer exist today. The answer remains one of astronomy's great mysteries, and mysteries are part of what makes the universe so wonderfully calming. There is no pressure to solve every question tonight. Simply knowing that such mysteries exist can be comforting. The universe does not demand that we understand it all. It simply invites us to wonder. So imagine yourself floating peacefully above the Milky Way, hundreds of billions of stars, slowly circling an invisible giant, hidden in the center. Everything moving with quiet elegance, everything following gravity's gentle rhythm. Everything exactly where it needs to be. Take another slow breath and drift even deeper as our journey toward the heart of black holes continues. As we continue our peaceful journey, we slowly drift closer to a black hole, not rushing, not falling, simply observing from a safe distance. There is no danger here, only curiosity. From far away, a black hole does not look unusual. There is no great whirlpool spinning through space, no giant mouth opening into darkness. Instead, you might see a region where the stars behind it appear strangely distorted. Light itself is taking curved paths, not because light has become tired or confused, but because space has been gently bent. Imagine walking across a perfectly flat field. Your path is straight. Now imagine the ground slowly becoming a deep valley. Without realizing it, your footsteps begin to curve. You are still walking forward, but the landscape has quietly changed. Light behaves in much the same way. It always follows the straightest possible path. Yet if space itself is curved, then that straight path appears bent around a black hole. This bending becomes extraordinary. Astronomers call this gravitational lensing. A black hole can act almost like a giant cosmic magnifying glass. Stars hidden behind it may appear brighter. Some become stretched into delicate arcs. Others seem to appear in more than one place because their light has traveled along different curved routes. It is one of nature's most beautiful illusions. Not magic, not trickery, simply gravity, quietly reshaping the journey of light. As we drift a little closer, another remarkable boundary appears. This boundary has an unusual name: the event horizon. People often imagine the event horizon as a solid surface. It is not. There is no wall, no invisible barrier waiting to stop you. If someone crossed an event horizon, they would notice nothing unusual at that exact moment. No flash, no sound, no sudden jolt. The event horizon is not a physical object. It is simply a point of no return. Outside this boundary, light still has a possible path outward. Inside, every possible future path leads deeper inward. Even light, moving at nature's greatest speed, can no longer escape. That is why black holes appear black, not because they absorb darkness, but because no light returns from within. Imagine standing on the bank of a slow river, far from a waterfall. The current is gentle. A strong swimmer can easily move upstream. Closer to the waterfall, the current grows stronger. Eventually, there comes a place where even the strongest swimmer cannot make progress against the flow. The event horizon is something like that, not because space is pulling you like a giant hand, but because space itself is flowing inward in a way that no outward journey remains possible. It is an imperfect comparison, yet a helpful one. Nature often allows us to understand the extraordinary through familiar experiences, long before anyone could gather evidence. Physicists wondered what time itself might do near such intense gravity. Einstein's equations offered a surprising answer. Time does not pass at exactly the same rate everywhere. We already know This is true, even here on Earth. Clocks at the top of mountains tick ever so slightly faster than clocks at sea level. The difference is incredibly small, far too tiny for human senses, yet modern instruments measure it every day. Gravity gently influences the flow of time near a black hole. This effect becomes astonishing. Imagine two astronauts. One remains far from the black hole. The other carefully approaches without crossing the event horizon. When the traveler returns, they may discover that less time has passed for them than for the friend who stayed behind, not because anyone was moving through time like science fiction, simply because gravity itself changes how time unfolds. The universe is far stranger than our everyday experience, and somehow that strangeness feels peaceful. It reminds us that reality is richer than imagination alone. If you watched someone approach the event horizon from far away, something curious would seem to happen. Their movements would appear slower and slower. The light reaching your eyes would become redder and dimmer. Eventually, they would seem to almost freeze near the edge, not because they had stopped, but because the light carrying their image takes longer and longer to reach you. To the traveler, everything feels normal. Their own clock ticks steadily. Their heartbeat remains unchanged. They continue forward without noticing anything special at the horizon itself. This difference between viewpoints is one of the most fascinating ideas in modern physics. Both observations are correct. Reality depends on where you are observing from. The universe is generous with perspectives. No single viewpoint contains the entire story. As you imagine this quiet boundary, there is no need to picture fear. Instead, picture stillness, an invisible shoreline between what can return and what cannot, a place defined not by violence, but by possibility. Beyond it, our current understanding begins to fade. Questions remain. Ideas continue evolving. Scientists still explore, still calculate, still wonder. And perhaps that is one of the most comforting truths of all. Even after centuries of observation, the universe still holds gentle mysteries, waiting patiently for curious minds. For now, we remain safely outside, watching as distant stars curve around an unseen giant whose quiet presence reshapes space, time, and light itself. Take another slow breath and allow your thoughts to become lighter as we prepare to discover how humanity finally captured the first image of something that cannot be seen. For centuries, black holes existed only in mathematics and imagination. Scientists believed they were real. The evidence grew stronger. Year after year, stars moved as though something invisible was guiding them. Clouds of hot gas spiraled around an unseen center. Light bent in curious ways. Everything pointed toward the same quiet conclusion. Something was there, something enormous, something hidden, yet no one had ever seen it. How could they? A black hole does not shine. It reflects no light. It gives nothing back. Trying to photograph a black hole would seem almost impossible. It is a little like trying to photograph silence or capture the shape of the wind. You cannot see the thing itself, only its effect on everything around it. For many years, astronomers dreamed of finding a way. The challenge was almost unimaginable. The nearest large black holes are astonishingly far away. Even the supermassive black hole at the center of our own galaxy lies about 26,000 light years from Earth. That means the light arriving tonight began its journey before human civilization had built its earliest cities. And yet, compared with other galaxies, that black hole is practically our neighbor. Trying to see it is like standing in New York and attempting to read the date on a single coin resting in Tokyo. The target is simply too small. Ordinary telescopes cannot resolve such tiny details. To succeed, astronomers realized they would need a telescope almost as large as Earth itself. Of course, building such a telescope was impossible, so they imagined something even more clever. Instead of one telescope, they would use many, across mountains, across deserts, across continents. Each observatory would collect tiny pieces of the same signal. Powerful atomic clocks would record the exact arrival time of every radio wave. Later, supercomputers would combine all those observations into one enormous picture. Together, the telescopes would behave as though they formed a single instrument the size of our planet. This remarkable project became known as the Event Horizon Telescope. It was less one telescope than a worldwide conversation. Observatories in Chile, Hawaii, Mexico, Arizona, Spain, the South Pole, and other locations, all listening to the same whisper from deep space. Weather had to cooperate. Equipment had to perform perfectly. Time itself had to be measured with astonishing precision. Even tiny errors could blur the final image. During observing nights, hard drives filled with data at incredible speeds, so much information that the internet could not carry it all. Instead, the storage drives were physically transported to specialized computing centers. Boxes filled with recordings crossed oceans and continents like precious scientific treasure. Months passed. Engineers, physicists, computer scientists, and astronomers worked patiently. They checked every measurement, compared every signal, built and rebuilt their calculations. No one wanted wishful thinking, only reality, only what the universe had truly revealed. Then, in April of 2019, the waiting ended. The world saw something no human eyes had ever seen before. A glowing ring surrounding a dark center, soft, golden, slightly uneven, simple, yet unforgettable. This was not the black hole itself. Remember, a black hole cannot be seen. Instead, the bright ring was hot gas, moving at astonishing speeds. Some of it circled clockwise. Some appeared brighter, because it was moving toward Earth, almost at the speed of light. The dark center was the shadow cast by the black hole, a place where light could no longer escape. It looked almost peaceful, not frightening, not violent, just a quiet circle resting within glowing light. Many people expected something dramatic. Instead, they found something surprisingly elegant, a reminder that nature's greatest wonders are often beautifully simple. The image came from a supermassive black hole inside a distant galaxy called Messier 87. Its mass is about 6.5 billion times greater than the Sun. Its event horizon is larger than our solar system, yet even something so unimaginably large appeared from Earth as only a tiny blur. Years later, astronomers completed another remarkable achievement. They revealed an image of Sagittarius A star, the quiet black hole at the center of our own Milky Way. This one proved even harder to photograph. Although it is closer, it changes much more rapidly. The glowing gas circles around it in minutes rather than days. Trying to photograph it was a little like taking a picture of a puppy that never stops moving. Scientists had to combine many observations while carefully accounting for those constant changes. Again, patience prevailed. Again, the universe shared one more secret. Perhaps the most beautiful part of this story is not the photograph itself. It is the cooperation behind it. Hundreds of people, many nations, many languages, different cultures, different backgrounds, all working together for a single purpose: to better understand a quiet object billions or even millions of light years away. Curiosity became a bridge across borders, across oceans, across generations. The photograph was not only a picture of a black hole, it was also a picture of what humanity can accomplish when people choose to explore instead of compete. As you drift a little deeper into restful thoughts, imagine that glowing ring suspended in perfect silence, light circling darkness, darkness giving shape to light, a reminder that even what cannot be seen can still leave a beautiful mark upon the universe. Take one more slow, comfortable breath. Our journey is carrying us even closer to one of the greatest mysteries of modern science. What truly happens inside a black hole? That is where our next chapter begins. The universe is wonderfully honest. Sometimes it gives us clear answers. Sometimes it quietly says, "I have not revealed this yet." Black holes belong to both stories. We understand a great deal about what happens outside an event horizon. The mathematics works beautifully. Predictions match observations. Experiments continue to confirm Einstein's remarkable ideas. But beyond the event horizon, our knowledge becomes softer, less certain, more mysterious. This is not because scientists have stopped asking questions. Quite the opposite. It is because the universe has carried us to the very edge of what present-day physics can confidently describe. Imagine standing on the shore of a quiet sea. You can see the waves touching the sand. You understand the wind, the water, the rhythm. But beyond the horizon, where the sea meets the sky, there are places your eyes cannot reach. The ocean does not become less real, only less visible. The inside of a black hole is something like that. We know there is an event horizon. We know gravity becomes extraordinarily powerful. We know nothing traveling slower than light can return once it has crossed. But what happens after that? Here, physics offers possibilities rather than certainty. According to Einstein's equations, everything that crosses the event horizon continues inward. Gravity becomes stronger and stronger. Space itself curves more deeply. Eventually, the equations predict something called a singularity. The word sounds mysterious, but its meaning is surprisingly simple. A singularity is a place where our current mathematics breaks down. It does not necessarily mean nature has broken. It may simply mean our understanding has reached its limit. Imagine using an old map to explore a newly discovered island. Eventually, the map ends, not because the island ends, only because no one has drawn the rest yet. That is what a singularity may represent, the edge of today's map. For many physicists, this is an exciting thought. Whenever mathematics stops making sense, it often signals that a deeper theory is waiting to be discovered. Centuries ago, Newton's laws described gravity beautifully. Then, Einstein revealed an even richer picture. Perhaps, one day, another idea will help us understand what happens inside a black hole. One of the greatest challenges comes from trying to unite two extraordinary theories. On one side, there is general relativity. It describes gravity, space, and time on the largest scales. Planets, stars, galaxies, the expanding universe. On the other side, there is quantum mechanics. It describes the smallest scales, atoms, electrons, tiny particles, dancing according to probabilities rather than certainty. Both theories are astonishingly successful. Both have been tested again and again, yet inside a black hole, they refuse to cooperate completely. It is rather like having two magnificent books written in different languages. Each tells part of the story, but no one has yet found the perfect translation between them. Physicists dream of a theory, sometimes called quantum gravity, a description that would gently weave Einstein's elegant geometry together with the strange beauty of quantum physics. Perhaps that future theory will finally explain what truly happens deep inside a black hole. Another question has fascinated scientists for decades. What happens to information? Imagine writing your favorite poem inside a notebook. The notebook contains information. If the notebook is burned, the paper changes. The ink disappears. Yet according to quantum physics, information itself should never be completely destroyed. So, what happens when something falls into a black hole? Does the information vanish forever, or does nature somehow preserve it in ways we do not yet understand? This puzzle became known as the black hole information paradox. It has inspired some of the brightest minds in modern science. Over the years, many possible answers have appeared. Some suggest information is stored on the event horizon itself. Others imagine subtle quantum effects slowly carrying information back into space. Still others believe an entirely new understanding of space and time will eventually resolve the mystery. For now, the answer remains open, and that is perfectly all right. Science does not fear unanswered questions, it welcomes them. Every mystery becomes an invitation to keep learning. As you rest, imagine countless researchers around the world, some working late into the evening, others watching the sunrise through observatory windows, some writing equations across whiteboards, others building instruments capable of detecting the faintest whispers from the universe, all connected by one simple desire to understand a little more than yesterday. Perhaps that is the quiet lesson black holes offer us. Not that we must know everything, but that wonder itself has value. Curiosity is peaceful. It asks gently. It listens patiently. It accepts that some answers take generations to unfold. As you drift deeper into relaxation, picture yourself floating far above a silent black hole. There is no fear, only stillness, only stars reflected across the endless darkness. The universe keeps its oldest secrets with remarkable patience, and one day, perhaps years from now, or centuries, or even longer, humanity may discover another small piece of this magnificent puzzle. Until then, the mystery remains quiet, beautiful, and perfectly at peace. For most of human history, the universe appeared silent. The stars twinkled overhead. Planets wandered slowly across the night sky. Comets came and went. Galaxies drifted through the darkness. Everything seemed peaceful. Everything seemed still. But appearances can be wonderfully deceptive. The universe is not silent. It has always been filled with gentle vibrations, tiny ripples moving through space and time themselves. For 100 years, these ripples existed only as a prediction. In 1916, Albert Einstein studied his equations of general relativity. Hidden within them, he discovered something remarkable. If massive objects accelerate, they should create waves, not waves through water, not waves through air, but waves traveling through the very fabric of space and time. Imagine holding a large, soft blanket. Two friends stand at opposite ends. Now gently lift and lower one side. Ripples move across the blanket. Everything resting upon it rises and falls ever so slightly. Einstein believed space itself could behave in a similar way. Whenever enormous masses move dramatically, they send tiny ripples across the universe. These became known as gravitational waves. The idea was astonishing, yet, for decades, many wondered whether such waves could ever be detected. They were simply too small. Imagine measuring a change far smaller than the width of a single atom. Now imagine doing that over a distance of 4 kilometers. That was roughly the challenge. Many believed it could never be accomplished, but curiosity is patient. Scientists continued working year after year, decade after decade. Engineers designed extraordinary instruments. Physicists refined their calculations. Thousands contributed their skills. Slowly, the impossible became possible. Then, on a quiet morning in September 2015, 2 detectors felt the tiniest of movements. One stood in Louisiana, the other thousands of kilometers away in Washington state. Both sensed the same delicate signal. Not an earthquake, not passing traffic, not distant thunder. Something far older, far farther away, more than 1 billion light years from Earth. 2 black holes had been dancing for millions of years. They circled one another, slowly, at first, patiently, each orbit bringing them slightly closer. As time passed, their dance became faster. The circles grew smaller. The speed increased until, during the final moments, they circled dozens of times. Every second, imagine 2 invisible skaters gliding across perfectly smooth ice. Each loop draws them closer together, closer, closer, until, at last, they meet, not with violence, but with perfect precision. The 2 black holes merged, becoming one in less than a single second. They released more energy than all the stars in the observable universe combined during that instant. Yet, by the time those ripples reached Earth, they were astonishingly gentle. They stretched our planet by less than the width of a proton. Tiny, almost unimaginable, and yet detectable. The instruments recorded a soft signal. Scientists sometimes describe it as a chirp. If converted into sound, it begins low, then rises quickly, a brief, gentle sweep, lasting less than a second. It was the first time humanity had not merely seen the universe. We had heard it, not with ears, but with careful instruments, translating the quiet language of gravity. It opened an entirely new way of exploring the cosmos. Before, astronomy depended mostly upon light, visible light, radio waves, infrared, ultraviolet, X-rays, gamma rays. Different forms of light revealed different wonders. Now, gravitational waves offered something new, a messenger that passes through Almost everything. Clouds of gas cannot stop them. Dust cannot block them. Even entire galaxies barely slow their journey. They carry direct information about events that would otherwise remain hidden forever. Since that first discovery, many more have followed. Black holes merging quietly across the universe, neutron stars colliding, space gently ringing with ancient echoes. Each detection adds another note to the universe's great symphony, not loud, not overwhelming, but subtle, elegant, patient. Perhaps that is one of the loveliest ideas in modern science. The universe has always been singing. We simply needed the right instruments to listen. As you breathe slowly, imagine those invisible waves passing peacefully through earth, through mountains, through oceans, through forests, through quiet cities, sleeping beneath the stars. They do not disturb the trees. They do not shake the oceans. They simply continue their endless journey, gentle messengers, traveling across billions of light years, each carrying a story from the distant past, a story written not in words, but in the quiet rhythm of gravity itself. And somewhere far beyond our galaxy, another pair of black holes continues its graceful dance, orbit after orbit, century after century, million year after million year, patiently waiting for the moment when space itself will once again sing across the universe. Take another slow, comfortable breath. The stars grow softer, the darkness feels warmer, and our peaceful journey through the gentle story of black holes continues. The universe thinks on timescales almost impossible to imagine. 100 years feels long to us. 1,000 years can contain the rise and fall of civilizations. Even 1,000,000 years is difficult for the human mind to picture. Yet, for the universe, 1,000,000 years is only a passing moment. Stars live for billions of years. Galaxies slowly change over trillions, and black holes may endure longer than almost anything else that exists. If you could drift forward through time without aging, the night sky would slowly begin to change. Not suddenly, not dramatically, just little by little. Constellations would gently dissolve. The familiar shapes, drawn by human imagination, would quietly disappear as stars continued their endless journeys. The Big Dipper would no longer look like a dipper. Orion would no longer carry his bow. Every pattern would slowly become something new. Even the Milky Way would not remain the same forever. Far in the future, our neighboring galaxy, Andromeda, will continue its gentle approach. Today, it is still more than 2 million light years away. It seems distant, almost unreachable, yet gravity never sleeps. Slowly, patiently, Andromeda moves closer, not because either galaxy is chasing the other, simply because Their mutual gravity draws them together. In about 4 to 5 billion years, their great dance will finally begin. Many people imagine a galactic collision as something violent, but galaxies are mostly empty space. The average distance between stars is so enormous that direct collisions are surprisingly rare. Instead, the two galaxies will slowly pass through one another. Their graceful spirals will stretch and twist. Long streams of stars will arc through space like glowing ribbons over hundreds of millions of years. The two galaxies will settle into one. Astronomers sometimes call this future galaxy Milkomeda. Its exact shape remains uncertain, but its beauty is almost guaranteed. And somewhere within that vast new galaxy, the two supermassive black holes will eventually find one another. Not immediately. First, they will wander through the newly merged galaxy. Gravity from countless stars will slowly steal their motion. Million after million of years, they drift closer. Eventually, they begin to orbit each other. At first, the circle is enormous. Each orbit takes thousands of years. Then, slowly, it shrinks. Gravity, once again, begins writing its quiet music, like the smaller black holes we visited earlier. These giants also send gravitational waves across space. The waves carry away tiny amounts of energy. Little by little, the orbit tightens. The dance becomes faster. The partners draw nearer. Finally, after an unimaginably long journey, they merge. One becomes two. Two become one. A new, even larger black hole rests peacefully at the heart of the merged galaxy. Its gravity guides the surrounding stars. The galaxy continues its slow, silent rotation. The universe moves forward. Trillions of years continue to pass. One by one, the remaining stars begin to fade. The smallest, red dwarf stars live the longest. Some may shine for trillions of years, patient, steady, almost eternal by human standards. But even they will eventually run out of fuel. The great age of starlight will slowly come to an end. The galaxies grow darker, not suddenly, just a little dimmer. With each passing trillion years, black holes remain. They become some of the last great structures left in the cosmos. For an unimaginably long time, they quietly collect the occasional wandering star, a lonely planet, a drifting cloud of frozen gas. Each arrival adds a tiny bit of mass. Each encounter is separated by immense stretches of silence. If someone could observe this distant future, they might think the universe had become almost perfectly still. Yet, even black holes may not last forever. In the 1970s, the physicist Stephen Hawking made an astonishing prediction. According to quantum physics, black holes are not completely black. Very slowly, they may release an incredibly faint form of radiation. Today, this idea is called Hawking radiation. It is so unbelievably weak that no telescope has yet detected it from a real astrophysical black hole. For the enormous black holes found in space, the process is unimaginably slow. A black hole with the mass of our sun would take far longer than the current age of the universe to completely disappear. Not billions, not trillions, but around 10 to the 67 years, a number with 67 zeros. It is so vast that ordinary language struggles to describe it. Supermassive black holes would survive even longer. Some estimates extend to 10 raised to the power of 100, a googol of years, long after every familiar star has faded, long after galaxies have changed beyond recognition. Only then would the final black holes very slowly evaporate, not with an explosion, not with a dramatic ending, simply a gradual fading, a whisper becoming quieter until, at last, it disappears. There is something deeply peaceful about that thought. Even the universe's greatest giants do not last forever. Everything changes. Everything flows. Everything belongs to time. As you continue to rest, imagine yourself watching this immense future from a place outside time. Galaxies drift like lanterns across an endless sea. Black holes shine only through their quiet influence. The universe breathes more slowly than any living thing, and in that vast silence, there is no urgency, no deadlines, no rushing, only patience, only the steady rhythm of a cosmos that has all the time there will ever be. Take another slow breath, feel the calm of the endless future, and allow yourself to drift even deeper toward peaceful sleep. As our final chapters still await that our journey draws gently onward, you may find yourself wondering, why do black holes matter to us? They are so far away, so quiet, so seemingly disconnected from everyday life. After all, tomorrow morning, the birds will still sing, the sun will still rise, the oceans will still follow the moon's gentle pull. Nothing about your day depends directly on a black hole millions of light years away, and yet, in quiet ways, they have shaped the universe that made us possible. Every great galaxy is like a living city of stars, hundreds of billions of suns, countless planets, clouds of gas waiting to become new generations of stars. For many years, astronomers believed that the supermassive black holes at the centers of galaxies were simply passengers, large but unimportant. Now, the picture has changed. Evidence suggests that galaxies and their central black holes grow together, almost as though they are partners in a very slow dance. When a young galaxy contains abundant gas, new stars are born rapidly. At the same time, its central black hole also grows as more gas spirals inward. The black hole becomes active. It begins to release enormous amounts of energy into its surroundings, not because light escapes from inside the event horizon, rather because the falling material becomes incredibly hot before crossing that invisible boundary. Sometimes this energy flows outward as powerful winds, sometimes as brilliant jets, stretching across thousands of light years. Those outflows can gently push nearby gas away from the center of the galaxy, and something surprising happens when too much gas is removed. New stars can no longer form as easily. In this way, a black hole may actually help control how quickly its galaxy grows. It is a remarkable balance. Too little activity, and galaxies might grow very differently. Too much activity, and star formation could almost stop. Nature often prefers balance rather than extremes. Even on the grandest scales, the atoms inside your body tell a similar story. The iron carried through your bloodstream, the calcium within your bones, the oxygen you quietly breathe. These elements were created inside ancient stars. Some of those stars ended their lives as black holes. Their final explosions scattered those precious atoms across space over millions of years. The material mixed with giant clouds of gas and dust. Eventually, new stars were born around one ordinary yellow star. A small rocky planet formed. On that planet, oceans appeared. Life emerged. Billions of years later, someone lay comfortably, listening to a bedtime story about black holes. The connection is astonishingly beautiful. We are not separate from the universe. We are one small expression of it. Carl Sagan once said that we are made of star stuff. Modern astronomy continues to deepen that beautiful idea. Every breath contains atoms older than Earth, older than the sun. Some are almost as old as the Milky Way itself. They have traveled through exploding stars, across interstellar clouds, into newborn planets, into forests, into rivers, into animals, into people. The atoms that form your hands may once have drifted through the glowing clouds surrounding a newborn black hole. There is something comforting about that thought. The universe is endlessly changing, yet nothing is truly isolated. Everything is connected through time. Even black holes, which seem to represent ultimate endings, can become the beginning of something new. The gas they help stir, the stars that later form, the planets that gather, the chemistry that follows, life itself. Scientists still debate exactly how important supermassive black holes have been in shaping galaxies. Every year, new observations refine the picture. Some questions remain open, others are becoming clearer. That is the gentle rhythm of science, not certainty arriving all at once, but understanding growing quietly. with every observation, with every telescope, with every patient calculation. Perhaps that rhythm has something to teach us beyond astronomy. Understanding rarely appears all at once. It arrives, one small insight at a time, like sunrise, brightening the landscape little by little. As you lie here, breathing slowly, consider how remarkable it is that tiny creatures living on one small planet have learned to understand objects millions and billions of light years away. Our ancestors looked upward and saw only points of light. Today, we can measure the dance of invisible giants. We can detect the faint ripples left behind when black holes merge. We can photograph the glowing rings around places where light itself cannot escape, not because humanity is finished learning, but because we never stopped being curious. That quiet curiosity is one of our greatest strengths. It asks without demanding. It observes without rushing. It accepts that nature reveals her secrets in her own time. As our journey moves gently toward its final chapter, allow yourself to imagine the entire universe as one vast, peaceful story. Stars lighting the darkness, galaxies turning gracefully, black holes holding ancient secrets, and somewhere on a small blue world, one listener resting peacefully beneath the same universe that inspired every chapter of tonight's story. Take another slow, comfortable breath. There is just one gentle chapter remaining, a final moment to drift among the stars before sleep quietly welcomes you. And now, our gentle journey through the story of black holes is coming to a peaceful close. There is nothing more you need to understand tonight. No facts to remember, no mysteries to solve. The universe is perfectly content to wait. It has waited for billions of years. It can wait until tomorrow. For now, simply rest. Imagine yourself floating gently above the Milky Way. The galaxy turns so slowly that its motion is almost impossible to notice. Hundreds of billions of stars move together in quiet harmony, each one following its own path, none of them in a hurry. Some are young, bright, and blue. Some are older, golden, like our sun. Others have already grown quiet, their long lives coming gently to an end. Far away, at the center of the galaxy, the great, supermassive black hole rests, almost unnoticed, invisible, silent, patient. It has watched generations of stars come and go. It has witnessed new worlds being born, ancient worlds growing old, clouds of gas becoming brilliant suns, suns returning their precious elements back to space. Nothing is truly lost. Everything becomes part of the next chapter. Gravity never rushes. Time never complains. The universe simply continues its endless, quiet conversation. Perhaps that is why space feels so calming. It reminds us that life does not always need to move quickly. Some things become beautiful because they take their time. The oldest light, reaching your eyes, began its journey long before human history. The atoms within your body have traveled through ancient stars. The oxygen you breathe has crossed the ages. The iron within your blood was forged inside a star that disappeared before Earth was born. You are not separate from the universe. You are one quiet note within its endless symphony. Tonight, perhaps you traveled farther than any spaceship. You visited the lives of giant stars. You watched black holes come quietly into existence. You floated near the event horizon. You listened to the gentle music of gravitational waves. You witnessed the first photograph of the invisible. You imagined the distant future when galaxies would slowly merge, and even the greatest black holes would one day fade into silence. And now it is time to come home. Imagine our galaxy slowly shrinking behind you, its spiral arms becoming a tiny swirl of soft light. Beyond it, millions of other galaxies fill the darkness. Then, they too become small points of light. Finally, only one tiny blue world remains, Earth, wrapped in gentle clouds, turning quietly beneath the stars. You drift a little closer, across oceans, reflecting moonlight, across quiet forests, across peaceful deserts, across sleeping cities, where countless windows have already gone dark. You continue downward through soft clouds, toward familiar places, toward home, toward comfort, toward rest. Feel the gentle weight of your body. Notice the slow rhythm of your breathing. There is nothing you need to do, nothing you need to finish. The universe will continue its patient journey while you sleep. The galaxies will keep turning. The stars will keep shining. The black holes will remain silent guardians of gravity, and morning will arrive exactly when it should. Perhaps tomorrow night, the stars will look a little different, not because they have changed, but because you now know their quiet story. And perhaps whenever you look into the darkness, you will remember that even the deepest mysteries of the universe are not frightening. They are invitations to wonder, to learn, to imagine, to rest. As your breathing becomes slower and softer, allow each thought to drift away like distant starlight. Let every muscle grow heavy. Let every worry become lighter. Imagine the universe gently whispering its oldest promise. There is time. There has always been time. There will always be time. So close your eyes, if they are not already closed. Take one final, slow, comfortable breath, and let yourself drift peacefully into deep, restful sleep. Good night, Earth. Good night, Moon. Good night, stars. Good night, gentle galaxies. Good night, quiet black holes. And good night to you. Sleep well.